Try one here just with this example with moles and volume. Okay, got the answer there, a little peek. Okay, it says moles, 2.45 moles of argon gas occupies a volume of 89 liters. What volume will 2.10 moles of argon occupy under the same conditions of temperature and pressure? So it's saying as long as things don't get hot or cold or whatever, what will the volume be? What's the expectation here? Will volume go up or down?
Down.
We think down, right? I would agree, right? We're taking molecules out. So we'll take the number of moles, 2.45 moles, over the volume, and we get 2.10 moles over volume, right? V2. And what's the algebra look like for that? Cross multiply and divide. So cross multiply and then divide by that 2.45. Cross multiply and divide. Somewhere around 76.3 liters, okay? That's not, it's called Avogadro's law. Avogadro, remember, is the mole guy, right? He's the father of all of that sort of research and information. So when we deal with things with moles, typically it has a connection to Avogadro. Mm-hmm.
So it doesn't have to.
In all of his studies in discovering Avogadro's number, right, and being able to calculate Avogadro's number, he discovered this principle. And he says that the volume of 1 mole of gas particles at STP is always 22.4 liters. Okay? That is for any element, any compound, anything. Any element or compound fits this principle, right? And it has to be at STP. That's the important part. When we say STP, what does that mean?
Standard
Temperature and pressure, right? So what is the temperature at STP? No, that's the moles, or that's volume. 0 Celsius or 273 Kelvin, right? And what's the pressure at STP? 1 atmosphere. Good. So when we see STP, we have to think, oh, I know the temperature is 273, and I know the pressure is 1 atmosphere, right? Those are just knowns, okay? So he says, right? He did a bunch of studies with different gases, and he understood that at these equal conditions, everything had the same volume. And so this principle becomes kind of a conversion factor for us. We're able to say that 1 mole of any gas is equal to 22.4 liters at STP. And so what this allows us to do is now, eventually, we're not going to do it today, we're going to be able to use this information to basically do stoichiometry type problems. Right? If we have this much gas to start out with and it reacts, how much gas can we produce, right? In terms of volume or in terms of moles. So we're going to be able to use this information eventually in some stoichiometry type problems, right? It just becomes part of our conversion factor. Just like converting from moles to grams or moles to molecules, now we can convert moles to liters using that number. Does that kind of make sense? Mm-hmm. Okay, so at STP, we know that these two things are related. But what happens when things are not at STP? When our temperature is different or our pressure is different? Okay, we're going to use another formula called the ideal gas law. Okay, so this is for when gas particles are not at STP. It gives us a way to determine what's its volume, how many moles are present, all of these types of things. So the ideal gas law is going to put together temperature, pressure, moles, and volume, right? All of these things we've been talking about, we're going to be able to look at it now in what's called the ideal gas law. Okay, and here's what it looks like. PV equals nRT. Go ahead and put this on your little formula sheet as well. So all of these variables should be recognizable to us. The only one that does not look familiar is the R. The R value is one we haven't seen before. And I didn't do a very good job earlier of making sure we understood that N is the variable for moles. I didn't do a very good job talking about that, but N is how we represent moles. Because why can't we use M?
Because
it's the number.
It could be mass. It could be meters, the unit, right? There's lots of different things that the letter M represents. So instead, it's N. But R is different. R is what we consider a constant. Yeah, go ahead, Caroline.
Capital M for molarity.
Yes, capital M is molarity, but we couldn't use it to represent moles because then it would mean molarity, right? It's just like it's represented in a lot of ways. R is what we consider a constant, and so it is something that we use every time we use the ideal gas law. We don't have to calculate it, but it's constant, and this is the one we're going to use. There's two versions of R based on different units, but this is the one we want. 0.0821.
And we don't copy the other one.
I don't think you need the other one. Nope. I would just do this one. If you want to store that number in your calculator as R, you could. It's not that big of one to plug in, so I don't think it's that big of a deal, but you could store it if you wanted to in your calculator. But here's what has to be true in order for this R value to work, okay? The units for this R value, these little boxes should be times. The units for this are liters times atmospheres divided by moles times Kelvin. That's what the unit is for this R value. And the way it comes about is essentially just rearranging this equation, right? Divide by NT, divide by NT gives us R, right? Atmospheres, liters, moles, Kelvin. So all I'm saying here is that in order for this R value to work, the units must be atmospheres, liters, moles, Kelvin. So these are the ones where we must convert. Before, we didn't have to move volume as long as they were the same, but this is a must convert. Do you see the difference? Okay, tell me what's the difference between this equation and the ones we saw yesterday or 2 days, whenever we had class. What's the difference? I think there's kind of one big difference between the ideal gas law and the combined.
Multiplication and division?
We're going to use multiplication and division, agreed, right? The algebra on it is not difficult. It's just multiplication and division. What do you think?
There's no, of the same variable on either side.
Yeah, good. I think there's no change that happens. This is not a before and an after calculation like the other ones were. The other ones had some sort of change. But this is a snapshot type calculation. So it's saying, in this set of conditions, what do we have? That's the difference. So when you're looking at these gas law problems and you're trying to figure out what equation should I use, well, this is the equation you use if there's no change that happens, right? There's not a final and initial volume. There's not a final and initial pressure. Does that make sense? That's the difference, I think. Okay, so this is the ideal gas law. This slide is just a representation of how R was calculated and how did that come about. They just literally rearranged PV equals nRT to solve for the R value, knowing that at 1 atmosphere and 273 Kelvin, 1 mole equals 22.4 liters, right? Knowing all of that information, they calculated it out, and this constant is what comes out of it. It allows us to keep all of our ratios intact while we're doing different calculations, right? That's really what that's for. So that's just for fun, okay? So here's some reminders about the ideal gas law. We're going to use this equation when we're only giving one of our conditions. We talked about that. R is a constant, so we're always going to know what that is. Did you write that on your little sheet, on your formula sheet?
That is constant.
The R value, did you write down 0.0821?
Yeah.
I'd go ahead and put it on there. That way, you know, R is equal to 0.0821. That way you just have it there for reference. We're going to use it pretty often, so I think you'll know it. But that way you'll have it on there, okay? And then we're just going to be given everything else to solve for one missing thing, just like all of our other problems, right? We're going to solve for one of those variables. Let's try one without the answer here. Okay. This says, calculate the pressure in atmospheres of 0.413 moles of helium at 16 degrees that occupies 3.25 liters. So let's check through our units, right? Actually, before I even do that, tell me, what's our question mark here? What are we solving for?
Pressure.
Pressure is our question mark. So, oops, not R. Pressure is our question mark. We know this is N, this is T, and this is V. Any red flags here?
The T is in Celsius.
Temperature has to be converted. So temperature starts out in Celsius, and we convert by adding
273.
273. Good. So let's go ahead and do that. Do we have calculators out?
Yeah.
289.
Thank you. 289 Kelvin. Okay, so now let's just plug it in. All right, P times V equals N R T. In these problems, a common error I see is that people end up dividing over the wrong way. So if I have this set up, okay, if I have this set up like this, 9.799, right? I need to divide this over.
Yeah.
Yep. It's just a common thing people got to get into a hurry, and then we divide the wrong way. So just be cognizant of that. So my pressure comes out somewhere around 3.02 atmospheres. I want to make sure everyone can do that in their calculator correctly.
Yes.
Okay. Okay, so for this one, we had to convert grams to moles, convert our temperature, convert our pressure, and we end up with like 63?
Yeah.
63.2 liters.